Well, we're lucky today to be able to talk with Kent Kernahan, the inventor of the technology and the business model with which we're using to deploy CHERP locally grown power project. We're very excited to be talking with Kent this morning because we were unable to get to his presentation at our board meeting. And so this is for all of you, 170 people who were with us on Tuesday night and we're disappointed not to be able to hear an update from Kent. So thank you for joining us today, Kent, and go ahead and give us your presentation on the latest updates.
Thanks, Devin. Okay, so this is the May 2020 update from idealPV. idealPV produces intellectual property. That is our main product, and then the real implementations of those things. So this thing we already know about. These are the two patents that have been issued that are being used in the CHERP locally grown power project. I want to point out this second one. I'm sorry, we're just navigating mouses. There we go. So the first one is FOZHS, and we all know about that. That has to do with hotspots. It enabled a new architecture panel that wasn't possible before. In order to get a patent on something, you actually have to be able to make the thing. And so without the elimination of hotspots, panels that don't have bypass diodes were not possible. However, with the elimination of hotspots, they suddenly became possible. And at the same instant that we filed for the patent on FOZHS, we also filed architectural patents on the panel, which we then delayed working through with the patent office until we actually had issued the patent on how to prevent hotspots. The thing that's critical here, that's really important, is that we don't know in the future what new technologies might emerge, and we don't pretend to have come up with the only way that one would ever solve this problem. So this second patent doesn't really require the first patent, just that it's there illustratively to say that's how we solve the problem. What we're saying in this second patent, and the claim is actually an equation, is that any panel that has so many cells in series that under reverse bias conditions, one of the cells would be damaged. That's what this panel covers. So it draws a very neat line at the edge of current hotspot mitigation technology, where if you do that and you've got bypass diodes, then you can proceed. You want to put one bypass diode on every cell, you can do that. However, even if the solution is different than ours for preventing hotspots, the panel that results from that has already been patented. And this is the patent architecture that CHERP locally grown power is going to produce. So in some ways, this patent is even more fundamental and broad than the original zero hotspot patent. It's just you can't have one without the other, without proving into the world that there's some way to solve this problem. Okay, so that's history. These are already done, they've been issued. There is another patent application that is published that can be found under our name, and that's First Responder Safe Solar. This appears to predate the rapid shutdown technologies that the solar industry is deploying. This is our version of rapid shutdown. And in particular, it's vastly simpler than the rapid shutdown that exists today. Currently, rapid shutdown requires coordination between the inverter and the solar panels and the electronics. In this case, it detects whether or not the inverter is present. So this is a solution that is very generalized and doesn't require any particular capabilities by any other equipment. It's simply the panel detecting that it's been disconnected and shutting down. And then there are 4 new applications. Now, we don't normally talk about stuff that you can't look up and you can't search. But because these things affect CHERP locally grown power, and you're bound to hear about them in some form or fashion, in just broad brushes, let me just describe these, even though they are not publicly disclosed up to this point. The first one has to do with redefinition of the solar panels after they're installed. Ideal PVs are actually software defined, and they can be redefined after they're put on a building. This is something that follows from having a computer-controlled solar panel in the first place. Potential induced degradation. It turns out that the #1 cause of power loss post-installation in solar panels is heat. And the #2 cause is potential induced degradation. And so we have technologies that we'll be fielding that will really eliminate the exposure of solar cells to this field. Why this is important is not for current generation solar cells, but for the next generation of solar cells. The next one is dynamic installation optimization. Without getting into the weeds on this, and we really aren't in a position to discuss this publicly yet anyway, what this does is allow for the entire installation to be optimized, not just the individual solar panels. And then the last one is pay-per-use authentication. Because the panels are smart, they have fraud protection features that, among other things, can be used for making the panels not function if they're stolen, or making the panels only function under certain conditions where electricity is being sold. Then, I can't really talk about net then. So idealPV has a continuous stable of new things that we're working on, have been working on for years, some of which are unpublished applications, some of which are ideas or things that we've prototyped, but at this point, we haven't taken to the patenting stage. So I mean, extremely active in moving the state-of-the-art forward. And of course, with the factory opening, we'll have even more opportunities to advance the state-of-the-art.
Let me take a second just to characterize what Kent just said for 1 second. This idea of a post-install redefinition alludes to the fact that these will be the first smart panel or upgradable panels in the world. So this is very exciting evolution in the technology.
Well, thank you for that. Okay, now the nuts and bolts. Yep, mechanical design, electrical design, thermal design, all that stuff. This is a representative drawing of mechanical design, of which there are many. But every last dimension has to be checked against regulatory requirements, checked against optical requirements and thermal requirements. And so this is an element, but that's kind of not as exciting. Then there's the 3D modeling. So this is in fact the Gen 5 board inside the Gen 5 all metal extruded steel case. And that, in fact, is dimensionally accurate. Every component, every wire, how the wires get routed, all of that stuff is present. Now, I'll just point out a couple of the features. For example, this is the ribbon coming up from the solar panel. This is the screw terminal that secures it to the board. These are the fast-on connectors that carry the current coming back out of the solar panel, the waterproof interconnects that take them out. If we look closely, you see this whole haze of white and all this stuff labeled. That isn't labeled for some robot. That is labeled so that people can actually see what components are where for assembly, for QA. And then, of course, we see that everything is spread out. And if we flip this board over, we'd see there's nothing on the back side of it. That makes the assembly that much easier. It's also worth noticing that this board is mostly flat. So there's a few parts here, transistors and their heat spreaders, and some capacitors, just a couple of inductors. Those can actually be made even in an intellectually disabled workforce setting, or in fact, right next door to the solar panel. So this is the first smart panel, and this is the first solution that has electronics that is designed to be manufactured all in a co-located factory. It's important to note that just as we're talking about the world's first nonprofit distributed microfactory, it doesn't mean that the technology isn't state-of-the-art. It is well beyond anything that's in production today, even though the whole design process and assembly process has been radically simplified. Honors to Devin, who developed that term. And then, yeah, since we've got 3D modeling and we know what color the cells are, we can take a look at them. The really only striking thing is that other people make solar panels that look largely black or gray by doing things like using black tabbing wires so they don't show up, and using black backsheet material so it doesn't show up, all of which, by the way, reduces efficiency. The reason you don't see those things is because our tabbing wires are so small at 1 millimeter, and our interconnects are so small at 2 millimeters that you really can't see them from a distance. And the cells are packed so tightly that they appear to be merging in as one with the frame. So actually, this is the highest aerial efficiency solar panel on the market also. But it's made in a completely conventional, inspectable way at our factory. Okay, so it wouldn't be an idealPV presentation if we didn't have a little mayhem. This is the worst case that happens with hotspots. But let's not talk about that. Let's talk about the best case. And really what I want to take you through on this particular slide is this idea of you start with something that's experimental and then it becomes done. This panel has been out in the field for 20 years. It's part of a actually worldwide study. Every climate, really every weather pattern, looking at what happens to solar panels as they age. So that area that we're pointing to there, that is 20-year-old EVA. That's the plastic encapsulate that exists between the glass and the solar cell. Now, that 20-year-old EVA has been heated by the sun and experienced solar radiation. And it's also been heated underneath by the electrical power coming back out of that solar cell. But there's nothing wrong with this panel. If anything, it might have a minuscule mismatch between one cell and another, but this is not a cell that was sitting under a tree or anything special. This is as good as it gets, if you will. That's also 20-year-old EVA. And it's been in the same sun with the same ultraviolet radiation for the same amount of time, for 20 years, in the same climate with the same weather. The only difference between that EVA and the EVA shown with the red circle is the heat electrical energy coming back from the cell. If we turn the contrast up and look carefully, we notice that this isn't just in that part that we could visibly see, it's actually everywhere. And this whole degrade process on this plastic is where the primary power degradation in solar panels actually comes from. But importantly, it isn't any place else. So what does this prove? Well, this proves that as far as idealPV is concerned, the process and materials are done, and they've been proven stable for decades. When you look at an idealPV under infrared camera, you're going to see that when it comes up and operates, the cells appear to disappear. That is, there's almost no temperature difference between them and the EVA in between them. And this picture shows you what the aging for a 20-year-old ideal PV is going to look like. That is, it's not going to look like anything at all. It will be pristine, just like all the areas that were not subjected to the cell heat are in this picture for a conventional panel. On the other hand, for the conventional panel, hotspots degrade all known solutions and even the proposed ones. In fact, there isn't a solution for manufacturing a panel that experiences electrical heating from the cells that holds up. They just slow it down a little bit. So what's experimental? Well, we're still waiting for that process technology and those materials that allow conventional hotspot mitigation solar panel architecture to survive for decades without degradation. And just so we're not looking at stuff that's 20 years old, here's one that's only 7 years old. Now, this also turns out to be a Walmart store. That first catastrophic picture is the other end of the hotspot picture where bad things happen and electrical arcs result. And in this case, you have 9 stores that had fires on their roofs. In this particular case, there's no fire. This cell is simply 7 years old. It's a more powerful cell than the 20-year-old one you were just looking at, but you can see the telltale signs of the same EVA aging process, only faster. And let's turn the contrast up on this one. What do we see when we turn the contrast up on this one? We actually see here a separation line. See how the EVA looks all cloudy in this area? So this cell is getting so hot that it's prematurely aging the perimeter, and the inside here is actually separating from the solar cell. That's why you can't distinctly see the solar cell anymore in this area. In fact, when this picture was taken, and it was taken for the court case between Walmart and Tesla, we think that the hotspot was actually operating and this EVA in the center may be molten. In any case, the problem is getting worse as technology advances. In fact, conventional solar's really gotten itself into a bad corner. Current cells produce at least 40% more power than those 20-year-old cells that we saw. And current solar degradation by recent studies that are only 3 years old, not 7 years old, show that the degradation rate is 5 times worse than it was 20 years ago. That means a projected loss of 40% over 20 years. That's not viable economically. In fact, back 20 years ago, the power loss over 20 years was only around 9%, which is what you saw in that first picture. But that's just where we are right now. Next generation cells more than double in power. And with standard architectures and really self-inflicted heating, there's no reason for this heating to occur for the solar panel produced power. This problem is just getting worse, and it's getting worse geometrically. So the new solutions that have been proposed kind of slow things down for today's solar panels, today's solar cells. They're catastrophically inadequate for the power levels that we're talking about with the next generation. You just simply don't have a solution in the solar industry for the kind of heat that's going to be generated when we have this kind of power density. And we shouldn't have to. The first law of thermodynamics, energy can be created or destroyed, only moved around and changed in form, says that these cells should be getting cooler. And in fact, on ideal PVs, they do. And the problem of encapsulant gets easier. We fully expect when we put advanced cells into ideal PVs that the area of the cell will actually be cooler than the areas in between, not warmer. And that's probably a good segue for what comes next. So really, there's a fork in the road. We're on this track, which can take us down into the spiraling corner of more and more heat as we try to improve the efficiency of the cells, or up towards simpler, more powerful, lower cost solar panels. So let's look at what's going to happen in 2025. By 2025, the power in each solar panel will have doubled from what we see today. The cost per panel will have halved. All hotspots will be gone. We won't actually think of solar panels as having hotspots anymore. The arc faults that cause these fires associated with the hotspots, they'll be gone too. The panels will be safe to handle because they'll actually turn themselves off when they're disconnected. And the glass, the silver, something like 20 bucks worth of silver in each panel, the lamination process, all these things will be obsolete. Okay, so I've told you what happens in 2025. I've got pretty good confidence that this is really what's going to happen, because every technology required for this to happen exists today. Some of them haven't been productized. Some of them can't operate at the temperatures of current generation hotspot mitigation panels. But all of these technologies are here. So we know what's going to happen in 2025 with FOZHS available. It's just a matter of productizing these new technologies. But what's going to be interesting is trying to imagine what will come next when that corner of the engineering box has been taken away, and now technologies we haven't even imagined might be practical suddenly are. So it's going to be really exciting. We're on the kind of curve that brought us the personal computer, the cell phone, advanced microelectronics that have gotten into our toasters. That's where we are with solar today. Thanks for your time.
Thank you so much, Kent. One of the things that got me most excited about talking with Kent 5 years ago at the very beginning of this journey was not only the technology that they've created to solve this current hotspot problem, but all of these opportunities that he's just mentioned that his technology unleashes. So it's the future R&D opportunity around the solar panels that we're now just starting to create this year in Pomona that got me most excited, when we can start eliminating the glass and go from silver to aluminum, a much more available and less expensive metal for all of the wiring. It's just very, very exciting to be on this adventure. And we just thank you so much, Kent, for all you've contributed to this.
You're welcome. It's been, it is just, I can't tell you how excited we are to see the progress by the CHERP locally grown power team and bringing this out to the world. We can only guess, how the solar industry and our cities are going to change as a result of this.
Yep, and it's happening pretty quickly at this point. So thank you so much.